Hello everyone, and thank you for joining today's webinar on response spectrum analysis based on ASCE code. Myself Surajit Ghosh. I am a senior structural engineer and I have been working in Bendler Systems in engineering simulation group. Today we are going to discuss about one of the method used for dynamic analysis, response spectrum method, and we will follow ASCE 716 code or IBC 2018 code. Now I will demonstrate how we can apply the response spectral load based on ASCE 716 code in this STAAD model. This is a 34-story concrete building. Overall height of the building is around 140 meter with maximum base dimension of 52 meter. There is a 3-story podium which mainly used for car parking and commercial purpose. My intention is to perform dynamic analysis for this building. There are several inputs that we need to specify for a response spectral load case. Along with that, we need to combine the dynamic load case properly with other gravity load case. How to do that? First, I want to add a dynamic load or response spectral load under a primary load case. There is no rule to specify dynamic load case under first primary load case like static seismic load. So we can add it under any new primary load case. In the response spectral dialog, different versions of ASCE 7 code is listed, and for this demonstration, I will use ASCE 716 code, which is the latest one. There are few inputs which needs to be specified. First, some information about the structure which is required to determine these seismic parameters. About the mapped acceleration parameters, zip code for this site location is 92887. If you have an active internet connection, you can use this value and program automatically finds out the SS and S1 parameters from USGS site. Else, you can provide the SS and S1 values directly, which are mentioned here. Coming to the spectrum table inputs, site class for this site is B. Depending on SS and S1 values and site class information, short period and long period site coefficient values are calculated automatically from table 11.41 and 2. You can manually change the FA and FB values, but that is not required. TL value can be computed from chapter 22. Here we will use the value as 8. Now, depending on the occupancy type of this building, risk category is 3, determined from table 1.51. Seismic importance factor is 1.25 as mentioned in table 1.52. Now to calculate the seismic design category from table 11.61, we need the SDS value. This can be calculated based on the SS and SMS value, and the value comes as 1.197 if we calculate it using these formulas. For this value, seismic design category is D. The lateral load resisting system plays a vital role for structural response against seismic load, and depending on this, seismic load on the structure is calculated, which is I by R into the spectral acceleration value. For this model, it is ordinary frame and shear wall structure, and from table 12.21, we can find that the response reduction factor is 4.5. So I by R value in either direction comes as 0.28. We need to specify this value as direction factor in both X and Z direction. We will consider only positive factor as negative directional load will be considered in the load combination cases. We are almost done with parameter specification. I am not using the missing mass correction for this model. Response spectra uses modal combination method to combine the modal responses from individual mode. There are several methods available like the CQC, SRSS or absolute method. If there is any closely spaced mode, then CQC method provide more accurate results. So I am going to use this one for this model. For this combination process, we lost the sign of the final response quantity and it is an absolute number. We can use signed response spectra with dominant mode option, and program assigns the sign of dominant mode to the final response value. And coming to the torsion inputs, we need to consider the accidental eccentricity value in both positive and negative direction. First, let me create a load case with accidental eccentricity value as positive 0.05 or the 5%. In next load case, we will consider this value as minus zero point -0.05. Note that the static eccentricity remains 1 for all cases. And finally, another spectrum load case with no torsion. This load case will be used for orthogonal effect consideration. So, these three response spectra load cases are created for x direction, load 1 and 2 considering accidental eccentricity value with positive and negative factor, and load 3 without considering the accidental torsion. I need to repeat the same process for z direction. In z direction, three separate load cases are created: load 4 and 5 with accidental eccentricity, and 6 without any torsion value. Rest of the inputs are same except direction factor, which is now specified for z direction with value 0.28. Next, we need to generate the orthogonal cases as suggested in clause 12.5. We need to create 4 load combination cases for each direction where the respective response spectral load case will be combined with 30% load from orthogonal direction. Consider x direction. First load combination should combine load case 1, which is the response spectral load from x direction with positive accidental eccentricity value, and 30% of load 6, which is no torsion load from z direction. Second combination is the load case 1 and 30% load case 6 from negative direction. So minus zero point -0.3 is the combination factor. This should be repeated for load case 2 and load case 6, considering the response spectral load from x direction with negative accidental eccentricity value. 4 load combination cases are created now for load case from x direction. Same needs to be created for load from z direction also. This time, load 4 and 5 is combined with load case 3 with factor 0.3. All total 8 load combination cases are created considering the orthogonal effects. These 8 are the final dynamic load cases that should be used in analysis and combination with other load cases. Finally, we need to combine these load combination cases with gravity load. Now, there is one very important aspect which we need to consider: the redundancy factor. As the seismic design category of this structure is D, so we need to assess the torsional irregularity for this model and accordingly determine the redundancy factor. According to clause 12.3.4.2, for seismic design category D with extreme torsional irregularity, it should be 1.3. And if the structure is torsionally stable, still it should meet two other criteria before reducing the value. So we need to first check whether the torsional behavior of the structure is okay or not. Program can check few irregularities of structure if check irregularity command is provided. From flow diaphragm option, we can select ASCE7 code and tick the check irregularities option. Note that this check is only performed if rigid flow diaphragm is specified in the model. For this command, for ASCE7 code, three irregularities are checked. First one is the torsional irregularity check. Second one is the reentrant corner check. And final one is the mass irregularity check. When you perform this check for any model, torsional behavior of the model is calculated. An unit load is applied in each orthogonal direction at the center of mass of diaphragm, and displacements of the two extreme ends of the diaphragm are extracted. The ratio of this is compared with the code limit, and if the ratio exceeds the limit, that is reported in the output. In the output, the details of each irregularity check is mentioned with details. For torsional irregularity, first the displacement of each diaphragm in x and z directions are mentioned, and then the ratio is printed. It is compared with 1.2 and 1.4, which are the limits, and the status is mentioned in the table for each diaphragm. For this model, there is no torsional irregularity noticed, and all diaphragms are okay. Though the structure is torsionally okay, still for safety consideration, we are considering the redundancy factor as 1.3. To consider this factor in analysis, there are two approaches. Either we can create 8 new load combination cases where the existing dynamic load case is multiplied with this factor. Else, we can use this as the combination factor for seismic load case during combining with gravity load cases. Say I want to generate a combination case as per ASCE 7 code where combination factor for dead load is 1.2, live load is 1, and seismic load is 1. For this model, load 7 is the dead load case and load 8 is the live load case. To create this combination using second approach, we need to combine load 7 with factor 1.2, load 8 with factor 1, and load 11, which is the response spectral load from X, with factor 1 into redundancy factor 1.3. This is the final load combination case, the result of which should be considered for member design. Same should be repeated for seismic load with combination factor minus 1.3. With this, we have considered seismic load from negative x direction. Similarly, we need to create the load combination cases for all directions. So, from 8 seismic load cases, 16 total load combination cases are created considering seismic load from both positive and negative x and z direction. Next, I want to discuss on how the dynamic analysis results are reported in the output and how to interpret the results. First, the eigensolution results are reported, frequency and time period values for each mode. Then, for each response spectral load, the results are reported separately. Consider the first load case, which is the response spectral load from x direction with 5% accidental eccentricity value. First, the modal weight values are reported in 3 orthogonal directions, which is the modal mass times g. For the selected modal combination method, missing weight is also reported. Next are the acceleration value for each mode and damping values. For response spectra for all modes, same damping is considered. The translational and rotational component for modal base results are also reported. Next is the mass participation factor. The mass participation for each mode along with cumulative mass participation till that mode for x, y, and z axis are reported in this table. This table is very important and we need to review the mass participation factors. I will discuss this in details. Base shear value is reported for 4 modal combination methods, though we have specified only CQC method as modal combination method. Peak story forces at each diaphragm level is mentioned next. Here, the story shear value in z direction is 0 as the load is applied from x direction only. Next are the torsional results. The plane dimension of the floor is used to calculate the accidental eccentricity value, which is 0.05 into plane dimension in perpendicular direction of load. Then it is multiplied with story shear value to calculate the accidental torsion of that floor. All these values are reported for each story level. Note that there are two additional text files stored in the same folder where the story shear values and eccentricity results are reported. You can also check the dynamic analysis results from the post-processing mode. After analysis, the results are available under Dynamics tab. You can check the time period and participation factor for each mode from the table. Also, you can check the mode shapes graphically for each dynamic load case. Results for individual mode can also be checked if IMR load cases are created from response spectra dialog. And finally, you can also check the animated view of the modes just to get an idea how the structure behaves depending on the applied lateral load for that particular mode. There are few things which we should check if we want to perform dynamic analysis for any model. First one is the mass participation factor. Code suggests that the overall mass participation in each direction should be at least 90%. If not, then we should consider higher modes till at least 90% mass is not considered in the analysis. We need to ensure that for this model also, whether 90% mass of the overall structure is excited for seismic analysis or not. This can be checked easily from the output file. In first response spectra load under mass participation table, we can notice that the mass participation in x direction is 82% and in z direction it is 79%. So for both direction 90% mass participation is not achieved. As I was saying, by default program considers 6 modes for dynamic analysis. Considering these 6 modes, 90% mass participation is not achieved and now we need to consider higher modes. This can be considered using the cutoff mode shape command. From miscellaneous commands, we can specify the desired mode number using cutoff mode shape command. Here we can specify any number and that many modes are considered for the analysis. But with increased modes, analysis time also increases. So we need to find optimum mode numbers which is required to get around 90% mass participation. Obviously, we can consider more number of modes, but normally it has been noticed that after 90% mass participation, if we consider higher modes, the change in mass participation is nominal. Now we can use the same model and increase the mode numbers. But as all load cases are considered for analysis, analysis time will also increase. If we perform 3 trials to get optimum mode number, each trial will take considerable amount of time. To reduce this, for this trial phase, we can use the same model without any load case and use modal calculation requested command which performs the eigen solution. You can say this is the first step before creating the response spectral load cases. As no other load case is present, so analysis time will be reduced. I have assigned 20 modes. Now we can check the output file, the mass participation table. Here you can notice that 90% mass participation is achieved in 11th mode for X direction and 13th mode for Z direction. Also, you can find that the change in mass participation reduces as we go for higher modes. For this model, we can use 15 modes for which 90% mass participation is achieved for both X and Z direction. Now, in the original model, we can assign the same. Finally, I want to discuss another point which is important for dynamic analysis: comparison of base shear with static seismic load case. If the base shear value obtained from response spectra is less than the base shear of static seismic load, then we need to find out the ratio and use it in response spectral load. How to do this? To compare this, we need to add static seismic load case. First, we need to define the seismic parameters from seismic definition window by selecting ASCE 716 code. We need to use same inputs like zip code 92887, TL is 8, importance factor 1.25, R value is 4.5 in both direction, and site class is B. We can specify CT and X values from table 12.82, or we can also skip, then program calculates the value internally. I have discussed the seismic definition part in my last webinar. You can go through the recording for more details. Now, static seismic load cases should be the first load case defined in a model. For this model, either you can create two fresh primary load cases where you can define the static seismic load and rearrange the load numbers. Or, similar to mode number selection, you can check this with the same model before defining any load case. I am using a copy of this model. First two load cases are static seismic load in X and Z direction with load factor 1 and without considering any torsion input, as that is not relevant for base shear calculation. Similarly, two spectrum load cases are added in X and Z direction with direction factor 0.28 as discussed earlier. After analysis, we can go to the output file and check the base shear values for static and response spectral loads. For static seismic load, the time period is calculated using the empirical formula using CT and X values, and if you compare it with dynamic load case, the fundamental time period is close to static load in Z but different in X direction. Base shear value for static load case is 6441 metric ton, and for response spectral load in X it is 1745. So the ratio is around 3.6. For Z direction, the base year is 1569 and ratio is 4.1. We need to use this as multiplication factor during response spectra definition. So in the original model, we need to multiply I by R value with this factor, which comes as 1 for X direction, and specify this as the direction factor. Similarly, for Z direction, we need to calculate the modified factor, which comes as 1.15, and specify the same as direction factor. Just one additional note. In this demonstration, I have not defined the mass model under any dynamic load case. Normally, we should define the mass model under the first dynamic load case. I have already defined a mass reference load case and specified all seismic weight under this mass reference load case. So, both for dynamic analysis and static analysis, seismic mass is considered from this mass reference load case. No need to define any further mass model or seismic weight. I have discussed in details about the mass reference load case and how to auto-generate this from dead and live load in my last webinar. You can check that session for more details. That's all from us today on response spectra analysis based on ASCE 7 code. Hope to see you all in my next session.